In this unit, we are reviewing the prerequisite skills that you need in order to be successful in AP Calculus. Now let's review expanding and condensing logarithms. This expression would be read log base 5 of 7, but you can have a base of e, which is a constant, which is approximately 2.72. Doesn't matter, you can have a base e, but when the base is e, we don't write log base e of 7, we write natural log 7. So if you see ln, that means natural log, and it means that you are dealing with base e. In calculus, it is natural log that occurs the most frequently by far. So I'm going to use natural log for all of my examples. There are three properties of logs you need to know: the product rule, the quotient rule, and the power rule. Let's start with the product rule. If I have the log of A plus the log of B, that is equal to the log of A times B. So there's your product rule. Here's a small example. If I had the log of 3 plus the log of x, that would equal the log of 3x. Going from a sum to the natural log of a product, this is considered condensing. But this is a two-way street. If I give you the log of a product, this can be expanded into the sum of two logs. In this case, the log of x plus the log of y. So going from the log of a product to the sum of two separate logs, this is considered expanding. The quotient rule. If you have the difference of two logs, like the log of A minus the log of B, this can be written as a single quotient, the log of A over B. For example, the log of x to the third power minus the log of x squared could be written as a single log of x to the third power over x squared. But of course this simplifies and you end up with the log of x. Again, going from two terms to a single term, this is considered condensing. But it works the other way too. If I had the log of x over 5, I could rewrite this as the log of x minus the log of 5. When you go from a single log to the difference of two logs, this is considered expanding. And then there is the power rule, which says that if you take a log and multiply it by something, it has the same value if you take whatever you were multiplying by and you make it the exponent. For example, if I have 1/2 times the natural log of x, according to the power rule, I can take this 1/2 and make it the exponent, and it would have the same value. So this would be the same as the log of x to the 1/2 power. And just for fun, let's remember that the 1/2 power is the same as the square root. In this form, when we go from having the multiplier in the front to suddenly having it as the exponent, this is considered condensing. But it works the other way too. If I had the log of x to the third power, if I wanted to, I could put that 3 in the front and it would have the same value. I could write 3 times the log of x. In this direction, it's considered expanding. So here's a combination of all three properties. First of all, notice that we have 4 factors here: the A, the B, the C, and the D. If we want to expand this, we're going to end up with 4 terms. So I'm going to have the natural log of A to the third power. This is positive because it is in the numerator. Think of it that way. I'm going to have plus the log of B. Again, this is positive because it's in the numerator. Now here's where the quotient rule comes in. We're dividing by the c term and the d term. So we're going to subtract when we expand this. So we will have minus natural log c and minus natural log d squared. So that's how you do a combination of the product rule and the quotient rule. Just any factors that were in the numerator will give you positive terms, and any factors that came from the denominator will give you negative terms. But what about the power rule? Well, we have the 3 and the 2 as exponents. Each of these can just jump to the front of their term. So the final fully expanded answer would be 3 natural log A plus natural log B minus natural log C minus 2 natural log D. For these first few examples, the directions are to expand as much as possible. So we will have the natural log of x squared plus the natural log of y to the third power. So this is our product rule at work. Now it's time for the power rule as I put the exponents out into the front. So I have 2 times the natural log of x plus 3 times the natural log of y. I want you to see this one as 3 factors. The x plus 3 is a single factor. It's 2 terms, but it's only 1 factor. In the denominator, I have this 4 and this y being multiplied together. So when I expand this, I'm going to have 3 terms. I will have the log of x plus 3, and I'm going to make that term positive because it came from the numerator, but then I will have minus the log of 4 minus the log of y. And that's all we can do. We don't have any rules that tell us something special we can do with the log of a sum. For problem C, using the product rule, we can rewrite this as the natural log of 3 plus the natural log of the square root of x. However, I would really like to use the power rule on the second term. So let's go ahead and view this as the natural log of x to the 1/2 power. Now I see that I can take that power and put it into the front. So the fully expanded form would be the log of 3 plus 1/2 the log of x. And it will not be fully expanded unless we put that 1/2 in the front. So that's mandatory. Let's look at problem D. There are 3 factors. So when we expand, there will simply be 3 terms. Log of 4 plus the log of x plus the log of y. That's really all there is to it. Problem B, let's start off with the power rule again. So these multipliers will end up as exponents. So that will give us the log of a to the 2/3 power plus the log of 2 to the 5th power. By the way, 2 to the 5th power is 32, so that occurs often enough that it's worth memorizing. So I'm going to go ahead and just write that. So I have a to the 2/3 power plus the log of 32. Now I am going to do the product rule. So we can write this as a single log, and I'm just going to be multiplying this times this. So of course it is traditional to put the number in the front. So I would probably write this as 32a to the 2/3 power. For this one, I feel the quotient rule coming on. We can write this difference as a single log of x over 2. And that's really all there is to that. Now, part D, we haven't really talked about this yet, so I think I need to do a little side lesson. For this last problem, we will need something called the change of base formula. If we have the quotient of two logs that have the same base, in this case, base b, you can rewrite them as a single log, which will not have this base at all. Instead, we will use these two values in the following way. One of these is going to become the base, and it's easy to remember which one it is because see how the base always is a subscript. The base hangs low. So look at these two values, the a and the c. See how the c is the one that's low? Well, guess what? It gets to stay low as the base. And then the a becomes the number that goes right here. So we have the quotient of two logs. Now it's a single log. So this is considered condensing. Notice that we started with both logs were base b, and suddenly it's now base c. So that's why they call it change of base. Because of the way the original base disappears when you do the change of base formula, it doesn't matter what the original base was, you would still get the same answer. So if I had log base e of a over log base e of c, it would still become log base c of a. Of course, we never write log base e. Instead, we write natural log. So if we have natural log of a over natural log of c, that will be the log base c of a. So we can use the change of base formula for problem D. Because we have the quotient of two logs which have the same base, they're both natural log. They're both base e. So according to the change of base formula, we can write this as a single log with a new base. Now be careful, because the base is changing, it will not be a natural log anymore. So we have to write log. So do you remember which one of these will become the new base? Well, it's the one that's already low, the 2, because the base always hangs low. The x goes right here, and that's it. We go from the quotient of two logs to a single log.